You hear me? Yeah. Check on your end.
Turn it off.
I can't hear you.
I said send you the file, you turn on the airdrop.
Oh, okay. Yeah, thanks. Yeah, I made my own like sort of notes and I sent them to Mitzilla's, but they're not complete
Okay.
and they're still kind of messy. So like, yeah, if I had,
You need to compare definitely.
yeah, it's good just to compare. Like I like Melissa's.
Okay, I haven't seen it yet.
Okay, so I think I mentioned this to Andy. So, I'd like to have an end of the year, for this class, an end of the year tea on Monday, not this Monday, but the following Monday. So on Monday, or this is a tentative plan, right? Yeah, so this is November 23rd. So I'll plan to sort of lecture for maybe an hour. And then afterwards, I was thinking that we can have, remember a table. We can go out to the area, the sort of grassy area out there, and we'll have food provided for you guys. So refreshments and coffee provided. If anyone needs tea, let me know. So as we've done all semester long, we will have safety precautions in place. Just like with the AMS conference, we'll have individually wrapped packages for the food, and we'll have paper cups for the coffee, and also normal social distance out there too. So Emily, did you see the announcement? Okay, good. All right. All right, so more details will follow. I'll actually send you an email with more details. All right, I think this probably will be one of the only classes that has offered face-to-face the entire time at UJ this semester. So you guys have a lot to be proud of. We can make it till Monday the 23rd without the university closing. All right. So what I'd like to do is I'd like to review a little bit. So let's review some of the ideas. So we're looking at the category of GRT modules. So as I mentioned before, we have various modules that we're interested in. So we have the simple modules. We know our hat lambdas. Where lambda is an exit T. Then we have the intermediate modules. So we have, let's see, nabla lambda, which is Z R hat prime lambda. We have the delta lambdas, which are just the co-induced modules. Okay, so we have these two types of modules. And then we have the injective. And they're also projective modules. And with the QR hat lambdas. Okay, so there are these four families of modules inside of this category. What did we show last time? So we had a theorem, and the theorem said the following. So we said that let M be a GRT module. And M as a ZR hat filtration. If and only if M, when restricted down, let's see, so this one is induced from B plus. So BR is, I guess, projected. Okay, I guess we want a finite dimensional. Right, so this gives a criterion for when a module has a Z hat filtration. And this is going to be well defined, so we can talk about the number of times This actually appears in the Z head filtration. And this number is well defined because all I have to do is I just take M. And if I restrict it down to BR, it's going to be projective. So it's going to be a direct sum of all the factors. So if I have M with restricted to BR, this is the direct sum over all the factors which appear in the filtration. Factors that appear. And all these factors are indecomposable over BR because they're just the projective covers of those one-dimensional representations. So ZR so this is hence indecomposable. Okay, so now you can just use Kroll-Schmidt. So the Kroll-Schmidt there. And so this decomposition over BR is unique. And because it's unique, this number is well defined. Okay, so now apply Kroll-Schmidt. Okay, any questions on this so far? Okay, now let's apply it to this module over here. So if this is an injective GRT module, and so it turns out it's injective over BRT and injective over BR. So let's see what happens when we do that. So this next part is called reciprocity. Okay, so consider QR happening. This is a injective GRT model. So it turns out that the induction functor well, let me just say this one. This is also a projective one too. We're just going to line it up with this. So it's both injective and projective. Okay, so now if I take the co-induction from let's see, VRT to GRT. This is exact. We saw that before. You can just write down a co-basis for GR in terms of BR. And so when I restrict this down to BRT, this is going to be projected. So QR at lambda restricted down to BRT is also projected. But then we saw that if you're projective over BRT, you're projective over BR. So QR at lambda over BR is also projected. Okay. All right, so now let's look at this number. So the number of times ZR hat mu is going to lie in a filtration. So this has a ZR hat filtration. Okay. So now we want to know how many times this ZR hat is in a filtration on any ZR filtration for this module. Okay, so as I mentioned before, we just have to know how many times this sort of sits inside of here as a PR module. Let's see. Yeah, as a PR module. All right, so now let's kind of keep arguing this way. All right, now remember this is the projective cover for mu, and this is projective as a BRT module. So I just have to know how many times this mu will actually sit inside of here, in the head or in the socle. And that'll tell me how many times this is going to be inside of here. So this is going to be the same as the dimension of the Hom space, BRT of Q over hat lambda with this mu. Okay. So you just look at how many times this mu appears in the top of this, and that'll pick off all these particular factors. All right, now you just use Frobenius reciprocity now. So this is induction from BRT to GRT. So this is Frobenius reciprocity. Okay. Now, it turns out that if I take a projective indecomposable module, and if I take any module, this counts a number, the Hom counts a number of composition factors. So this is an exercise. So exercise show that the number of times a simple module appears in a module is the dimension of its projective cover. Okay, for any algebra A. So I'll give you a hint, you just use induction on the composition line. Okay, and then note that this vector, the higher the x vanish, so it's going to be sort of exact on short exact sequences. All right. Okay, so now we can just apply to this. So this is a projective module over GR. This is the M over here. So that's going to be the number of composition factors. Okay, so this is going to be the number of composition factors in here. For this one. So let me keep going. So this is equal to ZR hat mu LR hat lambda. Now, it turns out that these have the same characters, so I can actually write this out. All right, so the upshot is, and we have a reciprocity. So I don't know what to attribute this to. I guess it first appeared. I'm gonna attribute to Humphreys. Notice this. So if I take want to know the number of times a Z, the Baby-Verma module, appears in the ZR filtration in terms of the Q's. This looks like the number of times the LR hat lambda appears as a composition factor inside. Okay, so this is really similar to the law that I gave in terms of injective modules in the G category, the H zeros, and so here I replace this by H0 or WOW module. Well, actually, I can replace this by H0, this being H0, this would be reduced. Okay, any questions on this? All right, so what I'd like to do next is I'd like to do an example. Why don't we just try to put this into effect here? Let's start with the simplest example for SL2. Okay, so this also works for GR. So remark that this reciprocity also works for GR. Okay, so you can actually just apply it to GR. The proof, though, needs the additional T structure. All right, so it's very hard to just prove this in the GR category. So you actually need to work in the GRT category and then come back down to the GR category to make this work. All right, so let's do an example. Try the nicest possible example. So let's do G equals SL2. And let's work with G1 modules. Okay. So what is lambda? Well, restricted weights go from 0 to P minus 1. Okay. And it turns out that, let's just focus on one of them. Well, let me just say it this way. So first of all, what is linkage? It turns out that lambda and mu are in the same G1 block. And only lambda plus mu is equal to P minus 2. Okay. Now, and then this lambda equals, so lambda equals P minus 1 is the Steinberg module. Is n its own block. All right. Now, you can write out the composition factors. Okay, so let's see. I guess we'll look at the ZR hat, the ZR lambdas. Okay, so these are the co-induced modules. And so this is co-induction from G1 plus the G1. And it turns out that L lambda sits inside of the head. It's the highest weight module. And the weights are lower if you go to the GRT category. Okay, so if I take lambda plus mu equals p minus 2, then basically ZR lambda has L lambda up at the top and L mu down at the bottom. Okay. And the dimensions are just lambda plus 1, right? So the dimension of this one equals lambda plus 1. The dimension here is also mu plus 1. Right? So the total dimension is lambda plus mu plus 2. And this is p minus 2, so it's p. All right, so the Baby-Verma modules have dimension p. And they have two composition factors like this. And in the case when lambda is equal to p minus 1, ZR p minus 1 rho is a Steinberg representation. Okay, we saw that. Okay, so it's not so bad to compute this out. And now let's look at the Q's. So we'll use this reciprocity law. So now apply reciprocity. All right, so let's just do the example when I look at Q of 0, for example. Okay. So let's see which VR mu's have to appear in here. Well, I just use the same reciprocity laws down here. And the only one which is going to be linked is the one when lambda is 0 and lambda is p minus 2. Okay, so these two Vermas lie inside of here. So Q1, 0 has factors Q1, so this should be a 1 here, sorry. So Q1, 0, Q1, p minus 2. Okay, so let me draw you a picture of what the Q1 looks like. Okay, so here's the picture. Okay, so if I take Q1, 0, well, I have to have this Z1 at the top. So I have an L0 here, and I have an LP minus 2. All right. So let me call this, let me just call this a plus here. Okay. Now, I also have another factor. I have the Z1 P minus 2 as a factor. And so I have to have a P minus 2 over here, and then I have to have an L0. Okay, so these are the two Baby-Verma modules inside. Okay, does everyone see this? And then I have to put other extensions on here. So this is a module which is self-dual. It has the trivial module at the top, the trivial module at the bottom. All right, and the heart is the direct sum of two copies of LP minus 2. Okay. Any questions on this? And so the other ones, I mean, for the other blocks, it's exactly the same, except for the Steinberg block. And so this is a picture for the trivial block. So let me just, I'll write out the other stuff. All right. So now, if I take Q1, P minus 2, I have L P minus 2 here. I have a L0. And then I have an L0 here. And I have an LP minus 2 here. All right. So I mentioned that we have a filtration in terms of the Z's. Okay. So this is going to be this circle represents the factors in this Z filtration. Now, it turns out that if I take the induced module, so the thing which are, so this is what the deltas of subsets. So there's also a Nabla filtration too, right? And that's why I'll indicate these extensions by negatives here. Okay? And when you do that, you get filtrations which go like this. Okay, so that's a Z prime filtration. So this gives you sort of the Z prime filtration. And if you want to put hats on things, you can. It sort of works the same for GRT also. Okay, so the dimensions of these. The dimensions of the projective covers are equal to 2p, right? We have p plus p, that's 2p. Okay? And this is for lambda not equal to p minus 1. Okay, and the dimension, of course, of the Steinberg line is equal to p. All right. Any questions on this? All right, so now let me give you some historical background on this. Was this ever mentioned in your category O class? Did they talk about the history of it? Okay, so you took a class on category O. All right. So who can tell me like when category O was like first came out?
Is that the early 70s?
It's like 1976. All right. Does any work sort of predate category O? Like did Bernstein, Gelfand, and Gelfand just like cook it up on their own?
All this stuff before.
What?
There's a bunch of stuff before.
Yeah, so for example,
Like just say Verma modules in general, and reducible motions and stuff.
yeah, well, I mean, they sort of developed this thing and they actually had this reciprocity law and everything, right? So was there any work which predated it? So let me be honest. I mean, this has always bothered me a little bit because there was work which actually predates, category O, and Bernstein, Gelfand, and Gelfand actually mentioned this in their paper. So if you look at their paper and you start tracing things back, the first example of things that were worked out was in this case that I just presented over here, which is SL2 situation. Now, to be honest, there are types of behavior that occurred for finite groups using what's called the Cartan-Brouwer triangle. So there's notions from finite groups using, I think it's called the CBE triangle. So, you know, things were motivated in some sense from finite group representations. All right, but for Lie algebras, the first work was done by Lee Pollock in 1967. So he actually computed out the projective indecomposable modules for SL2. So he computed structure of projectives for G equals SL2 and G, actually for G1. Let me say this one, G1 or G equals SL2. It wasn't quite stated in that language, but it's equivalent to looking at the first Frobenius equivalent. Right, and he actually fit, you know, he had a basis for these projective modules, and he saw that you can see from the basis and the generators and relations that there are going to be these filtrations that occur in the projectives. All right. Now, I've actually written a couple of papers with Dave, and so he's given me some stories. He never anticipated being like a research mathematician, and he's, you know, he wrote some things during his time as a research mathematician. But he never thought his thesis would really amount to very much. So he and Jim Humphreys were students together. So in 1971, Humphreys wrote a paper in the Journal of Algebra where he actually proved the reciprocity law for G1. At least he observed it. So this reciprocity law that I put up here, he actually observed back in 1971. All right, so then Bernstein, Gelfand, and Gelfand in 1976, they developed the category L. Okay, and they actually proved this reciprocity law in the category L for category L representations. And if you look at their paper, they actually give credit to Humphreys for the ideas. Right? So a lot of these ideas that happen occurred from finite groups and for modular representations, and they predate BGG. Okay. All right, now since that time that we have introduced the category O, there's been other developments. There's work of Rocha-Caridi. One person, so not two people. 1980, where she did stuff for generalized Verma modules. She proved this category OS or category OJ, and has the reciprocity law for those. As I mentioned before, there's more of an axiomatic approach to this by Ron Irving. A couple of papers on this. The big paper is by Klein, Marshall, and Scott, highest weight categories. That was 1988. Now, in the CPS paper that I passed out to you, they attribute this sort of reciprocity to Brouwer and Humphreys. Okay, so Brouwer sort of in finite groups, and then Humphreys for this situation. So they know the history of this. And I believe this is the first paper I wrote. So my collaborator Randy Holmes and I, back in 1989, we actually proved this when you have a triangular decomposition of algebras. So something like this, where you have like a zero part and you have a positive part and a negative part. So you have a triangular decomposition. So we looked at the question of filtrations, and we have reciprocity, sort of in this more general setup. And we can apply this to the algebras of cardinal. I haven't talked much about this. Right, these are the algebras which are simple Lie algebras and characteristic P, which have a triangular decomposition, but it's not symmetric. I mean, the negative part tends to be much smaller than the positive part. So you have to adjust your reciprocity rules accordingly in the case where you don't have the symmetry in terms of these parts. Okay, any questions on this? Okay. All right, so now I want to, I actually want to give you some preliminary information. So we're going to work towards the lifting conjectures. Okay, so towards. All right. Okay, so here we go. I'll just start motivating this in terms of some theorems and some results, and then we'll actually prove some of the theorems starting next week. Okay, so here's the basic question. So given projective module, let's say QR hat lambda, I guess I want this to be a restricted weight. So we'll take a restricted weight here. So given a restricted weight and a Q, then so does QR lambda hat, the structure, lift to Q. Okay, so what do I mean by this? I.e., because there exists a G module. Let's call it M lambda with M lambda restricted down to, let's say, GRT equal to QR hat lambda. So remember, GRT sits inside of G. Okay, so what we want to do is we want to lift the structure all the way to G. Right? Now we know that this works for irreducible representations. Okay. So no showed before that if L lambda and XRT actually lifts G. Okay, because we know that L lambda, when restricted down to GR, is equal to L lambda. So as long as you're in the restricted region, you're okay to lift to a G module. Okay, any questions on this idea? All right, so let me present a theorem. I'll talk about a little of the history of this theorem, and then I'll present Donkin's tilting module conjecture. All right, so here's the theorem. So let P to be bigger than 2H minus 2. Okay. And lambda next up. Then QR has lambda has a T structure. Okay. So I just mean the same thing as this. So it's a GRT module which actually lifts to G. It's the same as what I defined over here. All right. So let me give you a little history on this. Okay, so first I'm going to make a remark. So one can prove the G structure is unique. And that's because in the PR bounded category, this actually turns out to be a projective module. But I don't want to get into that. But I mean, essentially, that's how you prove it. We won't do that here. All right. Now, this theorem first appeared in the PhD thesis of John Ballard. So Ballard, in his thesis, I think it was around, maybe it was in the 1970s. I'm thinking like 73, 74, something like that. Okay. So he first proved the theorem for P bigger than 3H minus 3H minus. And then Janssen later on lowered the bound to 2H minus 2. This is the late 70s here. Prove this for P bigger than 2H minus. All right. Now, the amazing thing is that no one's been able to lower the bound since this time. Okay. So an open question to lower this bound. So this is part of the Humphreys-Verma conjecture. So it is an open question to lower this bound. For example, we'd like to know whether it's true for P bigger than H, for example. It's not even known in that case. Now, it is known in certain groups that this is true. So it turns out for G being equal to SL2 and SL3, this works for all P. So QR Ladhanda has G structure for all P. So for certain small groups, you can actually do this. All right, now, so this was kind of the state of the art in the late 70s. And then Steve Donkin came along and at this conference at MSRI connected these QR ad lambdas to token models. Okay, so now let me talk about Donkin's tilting module conjecture from 1990. MSR. All right, so first a bit of notation. So let lambda be a restricted weight. So what I have to do next is I have to sort of define lambda hat. So define lambda hat as 2 P minus 1 rho plus W0 lambda. Okay, so basically what you do is you add twice the Steinberg weight, and then you subtract off W0 lambda. You add W0 lambda. A lot of times W0 is minus 1 at the bottom. So in that case, you're just subtracting off lambda. So you take a weight, which is down here, and then your corresponding lambda hat is sort of above this. All right, so here's Donkin's tilting module conjecture. Okay. So let G be a semi-simple, simply connected algebraic group. Over K and characteristic of K. It's algebraic with characteristic. So then, let me just continue over here. So then, so this is just a continuation. So then, if I take the tilting module of highest weight lambda hat, and if I restrict it down to GRT, and I get QR at lambda. So Donkin's tilting module conjecture finds a SM lambda, describes it, and says that in order to get a lift of this, you can just take the tilting module of this particular highest weight. Okay. So, so it turns out that D-tilt, okay, so Donkin's tilting module conjecture is true for P bigger than or equal to, or P bigger than 2H minus 2. So sort of for the same reasons, this theorem is going to be true. But again, we don't have any sort of lower bound. We can't lower the bound yet. We're not in tilting module conjecture in general. Okay. All right, so the idea is next time, so I'm going to preview a little bit of the ideas for next time. So next time we're going to prove this theorem. So how are we going to actually prove this theorem? Well, what we're going to do is we need to construct something that QR hat lambda lives in. So we're going to do the following. We're going to take the Steinberg and we're going to tensor by some irreducible representation. All right. So now this is the G module. All right. This is an irreducible G module. This is a G module. The tensor bar is a G module. Now, when I restrict this down to GR, this is projective because the Steinberg is projective. This is also projective as a GRT module. Okay. So what we'll do is we'll take this QR lambda and we'll pick this one here. We'll pick the sigma such that this thing actually sits inside of this as a GRT module. And then when we break it up in terms of G summands, G indecomposable summands, we want to make sure that the G indecomposable summand inside of this one here matches up with this copy. And that's the idea of the proof. Right. And it uses some, weight arguments and everything like that. So the idea is you want to find G summand of M lambda such that M lambda restricted beyond the G. Okay, and that's what we're going to do in order to prove this. You would think, well, maybe you can adjust the proof to get the bound lower, but it turns out that no one's been able to do that so far. All right, any questions until this point? So next time we'll do the proof. Hopefully we'll finish the proof next time. And then, we'll do more with injective modules. And then I may talk a little bit about cohomology for Frobenius kernels. That should finish out the class. Okay, so let's stop here.
You happen to have a credit?
I have one upstairs.